Pattern matching, an exciting new feature that's coming to Python 3.10. But what is pattern matching and why should you care about it? Let me take you on a journey where we explore some of the thoughts and ideas that led to the design of pattern matching in Python. My name is Tobias Kohn and I'm going to be your guide tonight. It is surprisingly hard to give a clear-cut definition of what pattern matching is that works for all the varieties of pattern matching out there in the wild. But since pattern matching is the thread that holds all this talk together, let me try anyways. And for that, I want to focus on the three main tasks of pattern matching. It first checks the structure, the type or shape or whatever you want to name it of the data that you feed in, of your object, parameter, variable or whatever. It then selects code based on this shape or type of your object, of your data. Say you want to run code for if your object is an integer, and that might be different from the code that you want to run if you have a string or a tuple or a list or an object anyways. And it finally extracts the relevant pieces of information automatically from your object or input data and provides them in local variables for further processing. Say you have a sequence and you're only interested in the first and last elements of this sequence, then there's no need to keep all the rest. You just take these two elements, store them in local variables, and you continue the processing. That's the idea of pattern matching, or the extraction part of pattern matching. Let me illustrate all that with a very simple example. Let's assume we have two classes. The first class is to handle or to represent circles. The second class represents rectangles. Now, each of these classes has attributes for the position, x and y, as well as the size, which is the radius for circles, width and height for the rectangles. And your task is now to write a function, area, that computes the area of either of these objects. So you're giving it an instance of either circle or rectangle, and your function returns the area of that. How would you do that? Your code might perhaps look something like this. So you have this area function, you're given some shape, and first you check, is it an instance of circle, is it an instance of rectangle? Next, you then extract the relevant information from your object that you're given. In case of the circle, that's the radius, in case of the rectangle, that's width and height, which you store in local variables to then apply the mathematical formulas to compute the area and return them back. And now here's the pattern matching version of the very same code. You can see how this selection of the right code, this checking of what structure, what type does the input shape have, correlates with the extraction of the relevant pieces of information and storing them in local variables. So this one line, case circle, underline radius, says kind of select this code if you have something of type circle where I don't care about the position, but I want the radius extracted and stored in a local variable radius. In the case of the rectangle, we still don't care about the position, but we want the width and height extracted and stored in local variables wd and ht, and then the rest is the same as before. You apply the mathematical formulas and return the area that you computed for either shape. Since checking the type and selecting code based on the type is usually one and the same, we could say that pattern matching does two things for you. It selects some specialized code to handle and process data of a specific kind, of a specific type or structure, and it automatically extracts the relevant data or attributes information from the object that you provide, so that you can go ahead and concentrate on what's really important. Pattern matching is by no means a new feature, but has been around for about half a century, give or take, and is certainly older than Python. It just seems to be new to Python now that we introduced this feature. So let's have a brief look at the early beginnings of pattern matching and how it evolved to become one of the most popular features in modern programming languages. In the very beginning, pattern matching was some form of tuple unpacking. Sounds familiar? Of course, tuple unpacking is already part of Python's very fundamental core, and as such you could argue that pattern matching is nothing new to Python, which is extending those capabilities to be more powerful, more versatile now. But let's go back to our history lesson and look back at how tuple unpacking actually started. The goal was to create a minimalistic language, a functional language with strong static types where the compiler could figure out the type of every little piece of your code. The problem was, however, how to deal with tuples. A tuple can have elements of different types. In the example on the screen, we have an integer for the first field and we have a string for the second. If we now used some item access here, so we know that tuple 0 has type integer, tuple 1 has type string, but if we look at tuple I, we could not figure out the type of tuple I, whether it is an int or string, without knowing exactly what value I has. So this item access poses a problem to the compiler if it wants to figure out what kind of type every element in your code has. And the solution was to do away with this item access altogether and use tuple unpacking instead. However, if we're now dealing with dynamic data types, that is to say with trees or linked lists or something like that, we have another problem. In order for a linked list, we kind of link these different tuples together. In Python that looks as if the tuples following the first one are enclosed in the first tuple. However, even if you look in Python, the memory layout is a number of tuples that refer to each other in kind of a linked list variant. Anyway, the problem that we have to deal with is that we have an end marker. We have a non field at the very end, which is not a tuple anymore. That is, if we just use tuple unpacking, like you see at the very bottom of this slide. So we say x, rest equals mylist. We have the problem that if mylist finally ends up to be none, it doesn't really unpack into x and rest. So we have a problem there. We have an error. We have we can't unpack none to be two elements. How do we deal with that? The solution was to introduce conditional unpacking. Rather than just saying x, rest equals my list or tuple or whatever, I offer two cases. The first one, n, rest, applies if the given mylist data structure really can be unpacked into an n and a rest element. Otherwise, the case none statement is executed. It was discovered fairly quickly that patterns could be nested so as to express and represent special cases, which could then be handled separately. As you can see here on the screen, where we have a linked list with exactly two elements, m and n, followed by the end marker. If you then go one step further and try to handle arbitrary objects and classes rather than just tuples, you arrive at pattern matching in its modern powerful form, and how it is also included in Python 3.10 now. To summarize, pattern matching started as a feature for tuple unpacking and with the desire to handle dynamic data structures. Now, tuple unpacking and dynamic data structures really sound like something that's right up Python's alley, isn't it? With a basic understanding of what pattern matching is and where it comes from, we now face the challenge of properly incorporating pattern matching into Python. Despite the similarities between pattern matching and some of Python's core features, we still need to be aware that we're introducing a new paradigm of writing code, and hence tread lightly. There are three key aspects that I want to bring up in this context. First, the new feature needs to be isolated. The new pattern matching should not affect any code outside the match statement. Everything pattern matching related should be constrained to and limited to the match statement and not affect any code outside of that. Second, it should be familiar to Python programmers, but also to those who already know pattern matching from some other language. There's an entire world of pattern matching out there that we want to tap into, and we want to make sure that there's a smooth transition between pattern matching in the large and pattern matching used in Python. Whether you come from Python, you've learned pattern matching here and want to apply it and use it in a different language, or you go the other direction. For that, we want to use established syntax and conventions wherever possible. But we also want to use these established syntax and conventions from Python and honor Python's traditions and culture to whatever is possible. This means unavoidably that sometimes the two worlds will clash, and we need to find some compromise and trade-off in order to find a solution that works as good as possible. But we also acknowledge that this will probably not be the best solution for everyone out there, and some people will probably not be too happy with it. Finally, we also want this new pattern matching feature to be compatible with code that's already out there. You should not need to rewrite your entire code base or all your libraries in order for them to work with the new pattern matching feature. Rather, we aim for a gradual introduction, where by and by you write new code using pattern matching where it really shines and makes sense. This leads to some direct and immediate consequences. First, we need to introduce a new keyword, match, for this pattern matching syntax, so that the compiler has a chance to recognize at which point we are switching to this pattern matching world where we really want to use it, and if you don't use this match statement, match keyword, it will not affect anything you do. This means, secondly, of course, that match and case need to be soft keywords. They're not keywords if you're outside this match statement, and you can continue using them as variable names, function names, or whatever you want to. There are also some things that come up from Python's culture side. So with tuple unpacking or iterable unpacking in Python, the syntax using list with square brackets or tuples with round brackets for targets of iterable unpacking are both equivalent, and we want to keep something like that, even though it slightly restricts what we can do with patterns in the new pattern matching feature. And finally, although pattern matching is in most cases used in functional languages where everything is an expression, in Python, match must be a statement, as must the different case things, as Python is fundamentally a statement-oriented language, not an expression-oriented one. There are some issues that can inherently never be fully resolved because the conflict lies in the very nature of what we're trying to do, or how we look at things, or how we interpret things differently depending on context. Let me illustrate this with the example of how we use names in patterns to express different things. Usually, we would think of using a name in a pattern as an assignment target. However, if you look at the example that's provided here on the left-hand side, you can see that the intention was probably something different. So if we look at case pi here from a compiler's perspective, we would think that pi is a local variable and we want to assign the value of x to this pi here. However, if we look at the entire code, we can assume that probably the intention of the programmer here was to load pi from the math module and then have this first case succeed if x actually has a value that coincides with pi. The question then is, how do we interpret this case? Do we match only if x equals pi? That is to say, do we do a comparison between pi and x? Or do we match anything and set the variable pi to the value of x? So do we bind pi? These two semantics clearly clash, and it's very difficult for the compiler or interpreter to figure out which one to choose. If we have a language with declarations, so where we have to say var x equals something, or we say int x or whatever, in order to make sure that we are introducing a new variable at this point. We can then differentiate and clearly state, do we want to introduce a new variable at this point, or do we want to use an existing value and perform a comparison at this point? Other languages distinguish based on a spelling. If we use an all lowercase pi, for instance, that means that we want to bind it to the value of x, whereas using a capital P in pi means that we want to use the existing value and do a comparison instead. Another approach is to just bind local names and say that if pi as such is just a local variable, we bind it to the value that x has at a point, whereas if we write math.pi, what we mean is to use the value that's provided by this external symbol, by a symbol that's from a different module or namespace or whatever. And finally, we could just say we make all names binding targets. So irrespective of whether we write pi or math.pi or anything else, we always bind that symbol to the value that x has at that point. Clearly, none of these alternatives is really appealing and resolves our problem. However, we believe that the third here is probably the most Pythonic and the thing that kind of fits best into what we already have and think about in Python. Nonetheless, we fully acknowledge that this kind of issue is still exists, is unresolved, and probably not really resolvable in the first case. Of a very different nature is the issue where we have two names occurring in the same pattern, like here in the first case statement, case x, x. Now, if we approach it naively, that is to say, perhaps a beginner who's not too familiar with all of Python's features and intricacies, we could fairly assume, or rightly assume, that means that we expect a sequence of two elements which coincide. So for instance a tuple, where the first and second element in the tuple are equal. However, if you know Python and iterable unpacking, you might know that if you write x, x equals some expression, what will happen is that the first element of this expression is assigned to x first, and then the second element of this expression is assigned to x. So x only retains the second element of the expression provided, and the first one is just discarded. Which one should we use in this case? The one that's perhaps arguably more readable or obvious, or the one that more closely follows Python's existing semantics? Kind of the opposite problem occurs in the second case statement here, where we have 2 or n. Now, if we consider that we have a value that is 2 and we look at this pattern, then the first part here, the 2 equals 2, so this will already work and the pattern succeeds, the code below is executed and run. However, if the value provided is not 2, say 3.5 for instance, it will be assigned to n and then the code will be run below. The issue that we have in this case is that n might be undefined if the original value provided was a 2, otherwise n will be defined and have a specific value. So in this case, it's not quite clear what do we do, and could the program below even test whether n is defined or not in a meaningful way? Our solution to these two problems was to say that each alternative in a pattern needs to bind or define exactly the same set of variables, and each variable needs to be bound exactly once. So the first case statement here is actually outlawed because we would bind two different values or kind of bind to x 2 times. Whereas the second one would be outlawed because either we bind no variable at all or we bind to the variable n. Whereas both alternatives would have to kind of define the same set of variables in order for this entire thing to make sense. All in all, if we look at names in patterns, we basically came up with these 3 simple rules. First, all simple names are binding targets. Attributes, on the other hand, provide value constraints. This is to say, if you write math.py, you use the pi value there in order to compare it to the value that's given by the subject of the pattern matching. Whereas if you just write pi or anything, it will be bound to whatever value is provided. And finally, the set of binding targets needs to be deterministic. You just look at a pattern and you know exactly which variable will be kind of assigned to, will have a specific value if this pattern succeeds. For this last part, let's briefly express a possible vision of the future of pattern matching in Python, how this language feature might evolve and become even more powerful, versatile and malleable than it already is by introducing custom or bespoke patterns. Let's start this off by remarking that objects are complex beasts. There's more than one way to look at the structure of an object or to decide which attributes, properties or fields really make up the core, the essence of an object are important. That also means that we have more than one obvious way how to match a given object to the various patterns. And that leaves us some wiggly room where we can try and figure out how can we deal with these possible different views of one and the very same object. Let's look at a concrete example. A complex number is something that we can think of like a number in the plane in 2D, and we might express, as you can see here on the left hand side, say that this number here is 4 plus 3i. But we could also say that it has a distance of 5 to the origin and an angle of 33.9 degrees. So there's 2 absolutely equivalent different ways of expressing the very same object or the same number. And we might want to say in our pattern matching that we have a pattern for rectangular complex numbers where we use the numbers x and y for the coordinates, or we use a C-polar version where we have the radius, the distance to the origin, together with an angle. In this case, however, these rect and polar things are not really classes as such, but rather views of one and the same object. And what we might introduce in future versions is that we let a class define a specialized match function or match method that allows it to decide, given any object as, whether it's kind of matching that one or not. So in this case, for instance, crect might say, if I'm given a complex number, I return yes. This is kind of something that I recognize as that's a rectangular complex number. But I might also be given a 2D vector where I extract these 2 elements from the vector, create a new complex number and return yes. I can view this thing as a complex number that's kind of in plane, and I can compute with that. And if there's anything else, I return no. I don't know what this is or how to deal with that. And if we introduce kind of this flexibility, then there's a lot of additional things that we can do with pattern matching, and it really becomes a very powerful and very exciting tool. Pattern matching is based on some very simple and obvious principles, but don't let yourself be fooled by that, because they quickly lead to a very versatile and powerful tool that lets you write readable, succinct and efficient code. Of course, using that tool can become arbitrarily complex too. The real trick, of course, is how to fit pattern matching neatly into Python and its existing culture. I hope this presentation was able to give you some glimpse into the design process that led to the pattern matching feature coming to Python 3.10. Some of the involved trade-offs, but also some of the possibilities it opens up for future application development in Python. And with that, we come to the end of our journey tonight. Thank you.